Welcome, students. It's very nice to see you all again. Today is chemistry with teacher Mark. We are going to be doing electrochemistry. Electrochemistry should take quite a lot of weeks, but we are going to do it in 2 sessions. So we are going to do electrochemistry 1 today, and then next week I will do part 2. And this will include all of the information, almost all of the information for electrochemistry. I need to ask you a couple of questions first. Are you all confident about oxidation and reduction? Yes, maybe, or no? Oxidation, reduction. Just show me, students. Oxidation and reduction. Okay? Not quite sure, not sure. So Mary's. Glory, Silver Spring. Students, I need you to help me here. I need you to tell me oxidation reduction. Happy, mostly happy, unhappy. Great. Thank you, Glory. I saw some of you were this, some of you were that. That's okay. How about electrode potential, redox potential, reduction potential? Yes, maybe not, no. Okay, no from Mathari, no from Silver Spring. That's good. Thank you, Glory. Excellent. How about cell notation? That's where we write like Zn, then a line, Zn2 plus, then more lines. Yes, no? Cell notation, writing out what happens? No, mostly no. Okay, good. Thank you very much. Thank you very much, students. So I'm going to share my screen. There will be examples for you to do for each one of the examples that we do. Hopefully by the end of today, you will feel more confident. And then next week, we can do more exam questions and so on. So here we go. So I'm going to start with this. Electrochemistry, number 1, as I said. The syllabus is quite detailed, really. It has quite a lot of information. But what we're going to do today, don't write this down. There is no reason to write it down. What we're going to do today is the stuff in the first bit, really, to start with, number 3, and then electrolysis, particularly next week. So don't write that down. This is a question which has come out of a textbook, and it covers most of the information you need to know. Do not write it down. Do not write it down. But it asks you to identify anode and cathode, so we need to know what they are, to write half equations, to write what is happening totally, to decide what is being oxidized, what is being reduced, to show a diagram of it, to show how the ions and electrons move, to describe what is happening in it, number 7, to calculate the cell, although it shows you there, and to write the cell notation. Now, we're going to be doing quite a lot of this today. The ideas that you need to know about are these ones. These are all linked to electrochemistry. Don't write them down. Nothing to write down yet. The first thing we need to do, and this is a little competition for you, is to write down the reactivity series of metals. So what I'm going to do is I'm going to give you a few moments now to talk to your neighbor and see if you can write down the reactivity series of some metals in a table or in a list, starting with the most reactive and going to the least reactive, preferably vertically. Okay, so have a go at that just for a minute. Just see if you can write down the most reactive to the least reactive metals. Okay, I'm just looking for you to be able to do that. So everybody have a go, please. Most reactive to least reactive metals. Everybody have a go. Why can I not see my own screen? So somebody has got a very Mathari mix. That's really good. That's really very good indeed. Very fast. Well done. Well done, Mathari mix. St. Mary's is going, well, it's a nice day. I could be outside. I could be doing something more. Come on, everybody. I want to see the most reactive to the least reactive. It's very important. It's important for knowing reactions. It is important for extraction of metals. It is important in electrochemistry. So this is just the reactivity series of metals. Silver spring, may I have a look? Down a bit, please. That's in group 1. Yes, that's in group 1. I want to know some more. That's very good. Glory, well done. Very, very good. Well done. Excellent. Excellent. Some very good answers here. So let's have a look at it now. So everybody can look at it. So here is a list, if you weren't sure, of the reactivity series of metals. It contains most of the common ones. I know we can put in some that aren't here, lead, mercury, and so on, but these are the most important ones: potassium, sodium, calcium, magnesium, aluminium. It's worth remembering where carbon is. And I haven't put in hydrogen, but we need to know where hydrogen is, and that's between iron and copper as well. Okay, so if you didn't know that, it might be worth writing it down, but do put hydrogen just above copper. The next column shows how we extract the metals, and these top 5 here are all extracted by electrolysis. We will come across industrial electrolysis next time. The ones underneath are less reactive than carbon, and so their ores can be heated with carbon. Okay, so potassium, sodium, calcium, magnesium, aluminium. Carbon goes in, it's not a metal. Zinc, iron, hydrogen should be in here. Copper, silver, and gold. There are many, many other metals, but these are the most important ones. Okay, so let's move on. The second thing we need to know about is oxidation and reduction. So oxidation and reduction goes like this. I'm going to go through looking at oxygen, looking at hydrogen, and looking at electrons. Okay, oxygen, hydrogen, and electrons. So here we go. If you are looking at an equation, look at oxygens. If there are oxygens, is something gaining or losing oxygens? Gaining oxygen is oxidation. I'm sure most of you know this, but if you don't, it would be worth writing down. So if something picks up oxygen, then it is being oxidized. If something loses oxygen, it is being reduced. So here are 2 examples here. So Fe2O3, iron 3 oxide, here on the left-hand side, excuse me, in the blast furnace, reacts with carbon monoxide, carbon 2 oxide. The Fe2O3 turns into 2Fe. So the iron, the Fe2 here, has lost its oxygen, and therefore losing its oxygen is reduction. But the carbon monoxide, the carbon 2 oxide, turns into carbon 4 oxide. So it picks up 1 oxygen each. So it gains oxygen, and that means it is oxidized. This reaction is called a redox reaction. Well done, Glory. This is called a redox reaction because reduction and oxidation happen at the same time. The second way that we do it is look for hydrogens. So if the equation does not have hydrogens, does not have oxygens, look for hydrogens. Gaining or losing hydrogens is the opposite of what happens with oxygens. So if you gain oxygen, it's oxidation, but if you gain hydrogen, it's reduction. So if you lose hydrogen, it must be oxidation. Here's an example. This is ethanol. Okay, it's an alkanol from Form 4 chemistry. An alkanol, when it is oxidized, turns into ethanol here. If you count this up, if you look at the chemical on the left here, you will find that it is C2H6O. C2H6O. But the one on the right is only C2H4O, so it has lost 2 hydrogens. Losing hydrogen is the same as gaining oxygen, okay? At the bottom, going in the reverse direction, going from ethanol to ethanol, look, it has gone from 4 hydrogens to 6 hydrogens, and therefore it is gaining hydrogen. Okay, so gaining oxygen, losing oxygen, gaining hydrogen, losing oxygen. Sorry, losing hydrogen. The last way is looking at electrons and charges. And it goes like this. I'm sure you have come across oil rig. Let me just ask, have you come across oil rig? Have we got, do we know oil rig, Silver Spring, Glory, St. Mary's? No. Kabiro, have we come across oil rig? No. Okay. I'll explain it. So there are 2 different ways of remembering this in terms of electrons. Oil rig, like a rig for drilling for oil, or Leo, like the lion, goes grr. Okay, so oil rig, oxidation involves loss of electrons. Reduction involves gain. So oil rig, oxidation involves loss, reduction involves gain of electrons. Either remember that or remember this. This is Leo. Here it is, LEOGER. Losing electrons is oxidation, gaining electrons is reduction. Whichever one you like better, write it down. Oil rig or Leo goes grr. There's Leo. You've got a lot of Leos in your country. We have only ones in zoos here. Probably they shouldn't be in zoos. So oil rig or Leo goes grr. Both are okay. Doesn't matter which one you remember. It's just about remembering that gaining electrons is reduction and losing electrons is oxidation. Okay. So oil rig or Leo goes grr. This is silly, Leo. It's just the Latin for a lion, and grr is the noise that a lion does not make. You do not hear a lion going grr. It makes something much louder, but nevertheless, it's just a way to remember it. Okay, so let's practice those. Let's see if you can tell me whether these are oxidation or reduction. I'll give you all the answers in just a minute, but I want you to look at them and work out whether they are oxidation or reduction. So the first one, 2Mg plus O2 goes to 2MgO. Second one, could you mute, please, someone? Can you mute, please? Thank you. Here are the equations. I've got some equations here that you can look at. So let's try just those 3 to start with, okay? let's just have a go. See if you can tell me. The first one, Mg, the second one, CuO, the third one, Mg. Okay, so see if they are oxidation or reduction, or sometimes both, perhaps. See if you can work out which one is which. What do you think? 2Mg plus O2 goes to 2MgO. What do you think is happening there? Is that oxidation or reduction? CuO plus H2. Is that reduction or oxidation? Or both? Mg turns into Mg. Excellent. Well done, Glory. Very good. Absolutely correct. Now do the next one. Mg goes to Mg2 plus 2 electrons. Is that oxidation or reduction? Have a look. See if you can work it out. Well, this first one is gaining O. And so that is oxidation. In the second one, oh, sorry, Kabiro, let me just have a look at your answer. Kabiro, show me again. Good, yes, Kabiro. A little bit further away, please, Silver Spring. Ah, yes, yes, no, I did see it. Yet it was reduction. Good, excellent. Yes, yes. Well done, Silver Spring. The second one, let me see if I can just change my color. Hang on. Oh, come on. Right. The second one, CuO loses O. So that's reduction. But if you look at what is happening to the hydrogen gains oxygen, so it is being oxidized. This here, the Mg loses electrons. Well, losing electrons is oxidation, or oxidation involves loss. So that must be oxidation. What about some more? Let's have a look at some more. Let me just go. Oops, something has happened. So here's, oops, sorry. Here's some more. Have a go with these ones here. Here are some more here. So try with the Cu2 plus 2E minus goes to Cu. I hope you know that the E minus means electron. Okay. N2 plus 3H2 goes to 2NH3. That's ammonia from nitrogen and hydrogen. And then magnesium and copper ions goes to magnesium ions and copper. So see if you can decide what is happening in each one of these. Is this too easy for you, Wamuini? Wamuini students, can you do these? I hope you can. You need to decide whether it is redox or reduction or oxidation. In Glory, oil rig, what is happening to the Cu2 plus? You have to go back. Okay, let's just go back a bit because people are not getting this quite right. So I'm going to go back a couple of screens, okay? Okay, the first thing you have to know is that most of you have got this. If you pick up oxygen, you are being oxidized, okay? With hydrogen, if you pick up hydrogen, you're being reduced, okay? In electrons, look at this. Just try to remember this. Look at this bottom one down here. Losing electrons is oxidation. Losing electrons is oxidation. So if I have something like this, let me say I have Mg minus 2 electrons goes to Mg2 plus, then it is obvious that this magnesium is losing electrons, and losing electrons is oxidation. But if I rewrite this equation like Mg turns into Mg2 plus and 2 electrons, it's still the magnesium has still lost electrons. And if it has lost electrons, losing electrons is oxidation. Now, so you have to be careful that you can spot what is actually happening each time. So let's go on to the questions. So in this first one, that was easy. That one gains oxygen. That is oxidation. The second one, the copper oxide loses oxygen, and so it is reduced. The third one, Mg turns into Mg2 plus electrons. The Mg must have lost the electrons, and if it loses electrons, that is oxidation. In this one here, Cu2 plus 2 electrons, that is gaining electrons. Gaining electrons is reduction. So that one is reduction. Okay, so the first one here, this one here is oxidation. This one here, the magnesium is losing electrons. So that is oxidation. This one, the CuO loses oxygen. So that is reduction. And this one here, it is gaining electrons. The Cu2 plus is picking up electrons, gaining electrons. G, that's reduction. On the next one, what is happening to the N2? What is happening to the N2? Silver Spring, have a go. Silver Spring, I need you to try and have a go at this because St. Mary's, Glory, Kabiro, they are doing very well. Silver Spring, you really need to try and to work out what is happening so it is easier. It's not a guess, Kabiro. What is happening to the nitrogen? The nitrogen is picking up hydrogen. If it picks up hydrogen, then that is reduction. Okay, picking up hydrogen is this one here is reduction. Okay, that one's reduction. We'll leave the next couple. Okay, we'll leave those. We'll come back to them. The other thing you need to know is what a reducing and oxidizing agent is. So if X gives electrons to Y, then Y must be gaining electrons, okay? Remember, if it gains electrons, so Y is gaining electrons, well, G, E, R, it must be reduction, okay? And if Y gains electrons from X, then X will be the reducing agent. It makes Y pick up electrons. But if you look at what is happening into X, X is losing electrons. Well, L, E, O, Leo, that's oxidation. So if X is being oxidized, then Y is making it oxidize. So Y is the oxidizing agent. Okay. Kabiro, is this okay, nearly okay, or horrible? Glory, okay, on its way, good. St. Mary's, excellent. Wamuini, is this okay, nearly okay, or too much? Wamuini, Silver Spring, okay, thank you very much, Wamuini. Silver Spring, I don't think Silver Spring mean that, but anyway. Okay, Glory, we will do some more. Thank you. Thank you for being honest. Okay, so these are the ones which I said we would do, but we're not going to do them now. The other linked idea is some words, and cation, anion, anode, cathode. I'm just going to do a little bit of that now. I'm going to show you something which I think is quite useful. I may need to change my color. Sorry, let me just change my color of ink. Okay. I always write for my students, ions can be either cations or anions. Okay? So ions are charged particles, e.g. Cu2 plus, Cl minus, O2 minus, Na plus, and so on. Cations, I always write like this with a plus instead of a T. So that means A plus ion. So cations are positive. Cations are positive. And anions, I say it's AN ion. In other words, a negative ion. In other words, anions are negative. Now that is very useful. If you can remember whether something is an anion or a cation, that will help a lot. So I'm now going to just write down some ions, and what I want you to do is to put them into a little table just with the, let me just do something, sorry. So I want a table, and I want the cations on one side and the anions on the other. And these are the chemicals we are going to start with. So here are a group of ions, and I want to know, are they cations or anions? So you just take these and you write them down in cations and anions. Have a go. See if you can work out whether they are cations or anions. Everybody just have a go at that, please. So we can make sure we know which ones are which. Excellent, Mathari. Very, very good start. You've got it. Silver Spring, have we got an answer? Have we got some answers? Glory? St. Mary's, have we got some answers? Wamuini? If you have an answer, bring it forward, please. Bring it to the camera, please. Absolutely right, St. Mary's. Good. Well done, Wamuini. Very good. Well done. Good. Everybody's got that. That's excellent. I think everybody has got that. That's excellent. So all the cations are positive. So that will be Cu2 plus, Na plus, Ag plus, Fe2 plus, and all the anions will be negative. That's all these like that. Okay, that's good. Well done. Okay, the next bit that you need to know about is cell notation. In other words, how we draw the circuit. Okay, so here we are. Here is a circuit. Here is a circuit with two what we call half cells attached to each other. All right, it might be useful to draw it in just a minute, but not quite as detailed as this. So I'm going to show you how we do this. Okay, I'm going to show you how we do this. So on this side over here, all of this over this side and all of this over this side, this is called a half cell. And this one here is a zinc half cell. And over this side, there is a copper half cell. So the whole thing together is a cell. Okay. Now, cell really means like a little battery. Notice what it has in it. Okay. So in here, this is what we call the electrode. And the electrode is a rod. Okay. Then we have in here, we have the solution. And you will notice that they are linked. So the electrode is zinc as a solid, and the solution is zinc ions in solution. On the other side, we have a Cu electrode and a Cu2 plus Aq solution. Now, what is important about that is I will now redraw this on the next slide. Okay, so here we go. So I'm going to simplify it so you can draw it if you want to. So I have two beakers next to each other here. And into both of them, I put a rod, which is just a piece of the metal, which is just dipping. Oh, no. Which is just dipping into the solution. So here is the second one. Oops, what is happening? So it's dipping into a solution. In this one, I have zinc as a solid. And here I have zinc ions in water. This one, I have a piece of copper as a solid and a copper solution there. They are linked by a voltmeter. Okay. They are also linked by something between them, which you have to know a little bit about, which is a tube, and it is called a salt bridge. So if you were ever asked to draw this out, that is what you would draw. Okay, so that is it. So this is a lump of zinc. This is a lump of copper. This is a solution of copper ions, so it would be blue. You don't have to color it. I'm just showing you what it would look like, okay? Okay, so there is the solution. Now, zinc is more reactive than copper. So zinc more reactive than Cu. So Zn loses electrons because this is what all metals do when they react. So zinc loses electrons easily. So what happens is that the zinc turns into zinc ions and electrons. So in here, in the left-hand cell, the zinc turns into solution. It dissolves, okay? It just turns into the solution. That's quite a difficult idea, but it turns into the solution. And the electrons go round the outside, along here, through here, into here. And here, the copper ions pick up the electrons and turn into copper. Okay, the copper ions turn into copper. So the solid zinc dissolves and the copper comes out of solution. Okay. Now then we can put that together into what we call cell notation. Let's go back a slide. Here we are. There's the zinc in zinc solution. There's the salt bridge. Here's the voltmeter. Here's the copper in copper sulfate. Okay. That's what I've done here. I've just drawn it a little bit more simply. But what I've done here at the bottom is I've tried to say, look, if zinc is more reactive than copper, then because metals lose electrons when they react, the zinc will do it better than the copper. So the zinc loses electrons, turns into Zn2 plus 2e minus. It would be okay to write Zn loses electrons and turns into Zn2 plus. That would be okay. Now that means because it's losing electrons is oxidation. Okay, so it is being oxidized. This is gaining electrons, that's reduction. Okay, so that is being reduced. Okay, that is being reduced. So now I'm going to just change all that. So I'm going to get rid of the stuff at the bottom. You'll see what I'm going to do in just a minute. So get this idea. You know from the metal reactivity that the zinc is more reactive than copper. If it is more reactive than copper, then it is higher up in the reactivity series. It loses electrons more easily, and that makes the copper do the opposite. So I'm going to get rid of all of this. I'm going to show you what I'm going to write just now. Okay. So I look at this here. I know that Zn turns into Zn2 plus. And I know that Cu2 plus turns into Cu. Now, what we do is we do this. We say, okay, the zinc in a solid is a different physical state from Zn2 plus. So I draw a straight line there, and I draw a straight line here. This means different physical state. Okay? Different physical state. And in between the salt bridge, I draw like this, just dotted lines. Okay? That is what we call the state, the cell notation. Okay? That is a cell notation. I know this is difficult. Okay? I know this is quite difficult, but it's very important that you look at this and see if you can do it. So the one on the left, I've gone the zinc more reactive turns into zinc ions. Copper less reactive turns into copper. So Zn goes into Zn solution. And on this side, it goes in the opposite direction. In other words, the copper ions turn into copper on the rod. This is what I write here. So the solid line here means it is a different physical state, and the salt bridge is shown by this. Okay, let's see if you can do one. So here it is. This has zinc and zinc ions and silver ions. Look at what I have done here. That solid line means that this is in a different physical state from the solution. One is solid, one is liquid. Solid, liquid, straight line. Dotted line for salt bridge. And then the copper ions and the copper. See if you can do the same to this one here. I will do it in a minute. Just have a moment. See if you can write that cell notation for that one. I know this is quite difficult, but they are always worth a lot of marks, these questions. They are always worth a lot of marks. So it would be worth trying to do it. Wow, Mathari mix already. Wow, very, very good, apart from one thing. Only one thing wrong with that. Firstly, what is your name? But there is a problem with the charge on the silver ion. Oh no, oh no, oh no. Oh. Come on, St. Mary's, you can do this. Come on, Kabiro, I know you can do this. Wamuini looking cool, looking hard working. Let's have a look. Excellent. Really, really good. Well done, Wamuini. Very good. So Wamuini and Mathari mix both. Yeah, yes, I want to see. Yeah, show me. Is that a Jiraiya? Absolutely right. Absolutely correct. Glory, may I see? Show me. Show me. Bit closer, please. A little bit closer. Come closer. Picture. Hold it closer to the camera, please. Glory. St. Mary's, let me have a look. Lamech, your metal on the right is wrong. That is correct, St. Mary's. Ag plus is a cation. But see if you can write the whole thing. Glory, I think you had an answer. May I see it, please? No? Okay. Oh, what's that? Mathari mix is correct. Yes. Okay, so here we are. Here we are. Here's the whole thing. So I know that zinc is more reactive than silver. So the zinc will turn into zinc ions. And I know that the silver will therefore go the other way. like this. If I want to include the electrons, then it is either zinc loses 2 electrons to become Zn2 plus, or Zn turns into Zn2 plus and 2 electrons. Over here, Ag plus needs an electron to turn it into Ag. Anyway, Zn physical system change, Zn2 plus AQ, solid there, salt bridge, and then Ag plus AQ, liquid, phase change, Ag, solid. So if you got that right, really, really good. Well done. How about this one? See if you can draw a labeled diagram for this. See if you can draw a labeled diagram. I mean, like I did here. Okay, this sort of thing. Yeah, this sort of diagram. See if you can draw that sort of diagram for this one. And it has to be labeled so that you can show me what everything is made of. And Joe, fantastic. Really, really good. Well done. Well done. Well done, Glory. Well done, Joseph at Mathari Mix. Well done. Many students getting this right. Lamech, yes, we have to connect the silver and the zinc electrodes. That's very good, but you need to connect them with a voltmeter. Excellent. Kabiro, who's that? Kabiro. Very, very good. Well done. Well done. Anybody else want to show me their answers? Students are going very well today. This is quite difficult, but you're doing really well. Okay, I'll do it. I'll do it here. So I know that it looks like the iron is turning into Fe2 plus, and then the silver is turning it, silver ions are turning into silver. So I need to have my 2 beakers, 1, 2. Into my first one, I'm going to have a piece of iron. Okay, that's a Fe electrode. And it's into a solution of, in this case, Fe2 plus. It could have been 3 plus. That's an awful E. And on this side, I have another not very straight electrode, but this is a silver electrode. And I have a solution here, which is Ag1 plus AQ. I have a salt bridge which links them. You can always just draw it like sort of a little pipe or something like that. So there's my salt bridge. But I must remember, somebody forgot it, I must have my voltmeter between these two. Now, because you have drawn it like this is quite helpful because now I can tell you something. And that is that the electrons always move this way. So in other words, the Fe turns into Fe2 plus and drops off electrons. And these electrons go up here, through the wire, through the voltmeter, down the wire, into here. So they fill up this electrode here. And what happens here is that the Ag plus picks up an electron and turns into Ag. Now that means something important happens. And that means that this electrode here gets heavier because more silver is added to it. Now, if we go back to other ones here, oops, sorry, there, the same thing is happening. If I look at this one back here, the zinc turns into Zn2 plus and the Cu2 plus turns into copper. So if Cu2 plus in the solution picks up electrons and turns into copper, then it goes into this here, the copper electrode gets heavier. And again, the electrons are going to go this way round from the zinc to the copper. Now, sometimes they ask you that. Let's just go back quite a lot of slides. Look at this. We can now write the two half reactions. We can write the cell shorthand notation. Which electrode loses mass? Well, we know that the one on the right gains mass. We can see what the movement of ions is. We know the movement of electrons. We can tell what is being oxidized and what is being reduced. That is a lot of chemistry. So let's go on to where we were. Okay. So we have learned the linked ideas apart from one. And there is just one left, which is a little bit more complicated, but we just have 10 minutes, which will be enough to do it. It's about what we call electrode potentials. It is given a sign, E, with a little zero above it, or a little zero with a line, like the planet Saturn. So let's have a look at electron or electrode reduction potentials. They are written like this. Just take a moment to look at this. Just look at this here. You will see that there are a number of equations on the left-hand side. All of the reactions are written as gaining electrons. In other words, they are all gain electrons reduction. They are all reductions, okay? Don't write all this down, it's too much. We will write down a couple in a minute. So all of the stuff on the left-hand side is positive ions gaining electrons, reduction. Then on the right-hand side, we have some E0, that's redox potential, reduction potential, or electrode potential, what we call voltages. They're measured in volts. And I want you to look at them. Hydrogen here is listed as 0. Everything below it is positive, and everything above it is negative. look at where the most negative values are. These are very, very reactive metals. There's potassium, calcium, sodium. And down at the bottom are the very unreactive metals, copper, silver, and gold. There is a reason why lithium is at the top. It is to do with it being a very small ion. Do not worry about that. So in other words, the negative ones are the ones which are going the wrong way. Now, very, very important. We have to remember that metals lose electrons when they react. This is absolutely critical that you remember this. Metals lose electrons when they react. Now, that is really, really important that you remember that. Metals lose electrons. Now, if we look up the top, I'm just going to change my color. I'm going to try to change my color anyway. Here's potassium. Potassium does not want to pick up electrons and turn into potassium. Potassium ions do not want to do that. They really want to go the opposite direction. K wants to, look, lose electrons. So K would turn into K plus. So if it's written as K plus plus electron, that is not popular. It feels negative about this. Down at the bottom, Cu2 plus, not reactive metal, picks up electrons quite easily. That's because the other way round, Cu does not lose electrons very well. That is positive. In other words, if it is a negative number, it is not the right way round for these metals, okay? This is not good in that direction. Whereas these ones down here, which are positive, plus is good in that direction. Okay? That's really important. Now, let's have a look at zinc and copper. Remember, we had the zinc and copper half cells joined together. Okay, the zinc and copper ones joined together. In other words, that's the one where we had zinc in zinc ions attached to copper in copper ions. Okay, rubbish diagram doesn't matter. What we're trying to find out is what the voltmeter will read here. Here's my salt bridge. Okay. Now, look at these numbers here. Look at the electrode potentials. And it shows you that, let me just get my pointer on. Zinc here, Zn2 plus, turning into zinc, is negative 0.76. Copper, Cu2 plus 2 electrons, turns into Cu, positive 0.34. In other words, these two, let me just change my pointer. These two do different things. So this one on this side, this is negative 0.76 volts, and this one is positive 0.34 volts. Now that means, this one here means that zinc 2 plus ions plus 2 electrons and zinc goes in that direction, in the opposite direction. Now that is exactly what we found before. And this one, because it is positive, goes Cu2 plus 2 electrons, and it does go in that direction. In other words, the more positive one goes left to right, positive, left to right, more negative one, right to left. Okay? Now I'm going to show you something. We've nearly finished. I just need to remove, sorry, just need to remove all this ink. Don't worry if this is very hard. We will be doing this again next time. I will remind you of this next time. It is hard, but I think it is easier than you think it is. When you have seen it again, it will make more sense. So here are some things to remember. The more positive one goes forward. In other words, it goes from left to right. The less positive one goes backwards. Okay, so the more positive one, like in this case, copper, goes left to right, and the less positive one, the more negative one, goes right to left. If it goes backwards, change the sign. So I change from negative 0.76 to positive 76, and then I simply add them up. I'll show you that. I'll show you that now. So the more positive goes forward. So I find the more positive one. The more positive one is the one at the bottom, the copper. Okay, so the copper goes forward. So the Cu2 plus picks up the electrons and it goes to copper, and that is positive 0.34 volts. The less positive one, that's the zinc one, goes backwards. In other words, it's going to go, Zn goes to Zn2 plus and 2 electrons. And I change the sign. So if I change the sign, instead of negative 0.76, it's now positive 0.76 volts. And then I just add them up and I get 1.10 volts positive. Let's look at another one. Let's look at zinc and silver. Find silver, it's a little bit further down. So the most positive one is the silver. So the silver goes in the direction it is written, like this, and its value stays as positive 0.80 volts. The zinc is less positive, so it goes backwards, that is Zn, turns into Zn2 plus and 2 electrons, and we change its sign. So it's positive 0.76 volts. So this makes 1.56 volts positive. This is how we work out what a battery will produce in voltage, by pairing up the metals. Okay, more positive goes forward, less positive goes backwards. If it goes backwards, change the sign, add them up. So here it is in detail. So, whoops, there it is. So the zinc will go from right to left because it is more positive. The copper will go from left to right because it is the most positive. Change the sign on the zinc, add them up. These are the sort of questions which you might get. We're going to be doing them, having a look at them next time, but I'll show you very quickly that this is actually, whoops, quite simple. Let me just change my pointer. Okay, So we are looking for the most positive one. The most positive one is this one here. That means that this one will go in the direction which is written. PB2 plus turns into PB, and it stays as negative 0.13. It's not positive, but it's the most positive. Whereas the other one goes in the opposite direction. So it goes from Mg to Mg2 plus. And we change the sign on its value. So it becomes positive 0.76 volts. And that makes 0.63 volts. And that's the whole thing. That's the whole way to do it. Okay, that is a lot of hard work. That is a lot of hard work, and I appreciate your attention. Students, very, very well tried. If you got any of that, that is brilliant. We will go through it all next time again. We will review